So today's lecture, I was thinking we'd discuss open strings and T-duality, the interplay between T-duality and open strings. Still in the bosonic string. Then the next lecture, I will we'll go through how everything we've talked about, T-duality, orbifolds, and open strings, and T-duality, and so on, carries over what the fermions do. They play basically no particularly important role. But I'll describe the not very important role they play to you in the next lecture. Okay, but just not so as not to get distracted. Let's see all the phenomena first in the bosonic string. Okay, so consider. Let's say that we've got a circle. Okay, so we've got x is equal to x plus 2 pi r. Our action is 1 over 4 pi alpha prime d to sigma del alpha x. Okay, and now, so we've studied the circle theory in great detail, but we've always assumed so far that we had closed strings. Now, suppose we've got an open string on this theory. Okay. So we've got some open string, the sigma belongs to 0 to pi, and as usual, we have del sigma x at 0 is equal to del sigma x at pi is equal to 0. These are the Neumann boundary conditions that the string that we've always looked at while studying open strings. Okay. Now, a really important thing, I mean, the thing that gives all the fun when we're studying open strings on the circle is the following fact. Okay? Is the fact that the massless modes of open strings include a gauge Wurzel. Okay? So as you know, the
Wilson loop.
What?
A Wilson loop.
Exactly. That's what's going to be important. So as you know, the operator del x or del bar x for the closed string give you gravitons b, mu, nu, and phi. Okay, but the corresponding there's only one operator because del sigma is same as del bar sigma because the reflection condition. By the doubling trick, there's just one del x, for instance, and that corresponds to the gauge field. Okay, this you remember. Now, the question we're going to ask is the following. Suppose I turn on a uniform gauge field on my circle. This is what Manu was talking about. So I turn on some value of a mu. This is the a mu that is caused by this del sigma. Here is the field dual to this vertex operator. Okay, now how does it affect the physics of my open strings? Okay, so the first thing to remember is, now first let's forget about a mu. The first thing to remember is that we've got the open string, we've got the 0 mode, and we've got the oscillators. Okay, the oscillators are unaffected by the fact being periodic, as usual. The 0 mode is affected, but in the open string sector, not through winding modes. Because the open string is just, it's open.
It can't wind.
It doesn't wind. Okay? So not through winding modes, but only through the effect on the 0 mode by making the 0 mode periodic. Okay? So if you quantize the open string on a circle, then the only effect of the circle is on the 0 mode sector. And the only effect on the 0 mode sector is not by adding new sectors to the 0 mode, like the winding mode. It's just by making the momentum periodic. Okay? It's just the usual quantization except that P is equal to N by R. And that's the end of the story. So everything we did for the open string before goes through unchanged except that the momentum has to be N by R. This is clear, right? Now, Now, what we are going to, we're going to be studying open strings with Chen pattern factors. You remember that the Chen pattern factors, there's an I here, a J here, and in general we've got a UN gauge field. Okay? Now, the first question we can ask is the following. What kind of Wilson lines can be turned on in UN? So a Wilson line, by definition for me, is a configuration of the gauge field that classically carries zero energy. Okay? So this is a configuration, since classically the only energy in a gauge field comes through the field strength squared, it's a configuration such that all field strengths are zero. But in a non-abelian theory, there are two ways of getting a non-zero field strength. It's del alpha A beta minus del beta A alpha plus or minus whatever I A alpha A beta. So one easy way of getting zero energy is to make this zero and to make this zero. And you can show that that's the only way, or gauge equivalent to the only way. Okay, this is zero, made zero by just making A constant. Doesn't depend on X. And this is made zero by making the various constant A's commute. Okay, so if you've got many different A's, you can simultaneously diagonalize all the A's. In general, a classically zero energy configuration is one in which A's are constant and all commuting. This is generally true. In our situation, things are even easier, because at the moment we've got just one A in just one direction, namely the direction of this compact X. So there's not, this part was trivial, because A with A is always zero. Okay? So we just need to make these guys constants. Okay? So the configurations we're going to study are those configurations which classically have zero energy. Okay? They're configurations which have F alpha beta equals 0. Okay? They have F alpha beta equals 0, and they're configurations in which A, now I'm focusing on the case at hand. So we went through the general theory of how to do it when A is turned on many different directions. That will be relevant if we're studying two circles or more compactified. But in the case at hand, there's just one A, so we'll specify to that. That's Aij, let's call it. These are the matrix indices. It's some constant guy. Any A can be diagonalized by gauge transformation. Any constant A can be diagonalized by gauge. So let's say that this is alpha 1, alpha 2, up to alpha n. Okay? Such a background at the classical level will be as good a solution to string theory as the background in which A's are all zero, simply because classically these are all zero energy configurations, or locally they're all pure gauge configurations. How do I know that they're locally pure gauge configurations? I know they're locally pure gauge configurations because any configuration in which all the field strengths vanish can locally be put in the pure gauge form. That's some theorem of mathematics. Right? Any gauge configuration in which F alpha beta in a neighborhood is 0 can in that neighborhood be turned into the pure gauge form. Okay? Whether you can sew it up over the whole manifold or not is another issue. Okay? But, what that will affect, we'll see how that works. But at least classically, it has zero energy, and locally it's in the pure gauge form. These are related statements, because classically you only get energy from local quantities squared, and if it's locally pure gauge, then obviously it's 0. Quantum mechanically you can start seeing holonomies, because when you quantize something, we'll see how that works. Okay? Great. So now what we're going to do is to study open strings on a circle, let's say with n Chen pattern factors, on a circle in which we've turned on gauge holonomy of this form. And maybe it's more convenient for me to turn on Aij 2 pi r Aij is equal to alpha. This is just a matter of definition. Okay? You'll see why this is more convenient. Yeah, it's the holonomy, exactly. Okay. So now the question we're going to ask is, how is the quantization of open strings affected by the fact that we've got this holonomy on? Okay. Now, how is it affected? Well, in order to look at that, let's look at a little toy model first. Suppose we just have a U1 gauge theory on a circle, a U1 theory, and I've got a charge scalar field. Okay, plus F mu nu. Charge scalar field with charge 1, F mu nu, F mu nu. And this theory lives on a circle. This field theory lives on a circle. And around the circle, we've got a holonomy of this form. Okay? The holonomy is, since this is U1, we have 2 pi r A is equal to alpha. Okay, here we're going to have a more complicated version of this toy model. But let's look at the toy model first. So the question we're going to ask is, maybe let's make it even simpler. Let's look at just non-relativistic quantum mechanics. Let's think of this as the Schrodinger equation. Schrodinger equation for a particle coupled to a gauge field, background gauge field, so we can forget about this F mu nu. Let's make it even simpler. Let's make it the Schrodinger equation for a particle. So we've got just So in fact, let's imagine we've got a particle. Okay, so we've got a particle such that it's Lagrangian. Okay, its Lagrangian is m by 2 x dot squared, so x dot minus EA. How does it go?
No, P minus EA squared, but not x dot minus EA.
P minus EA squared. Thank you. Sorry. Yes, exactly. Sorry, just a minute. Yeah, x dot minus I minus EAI, the whole thing squared, and then plus some x0, which we don't care about. Okay, this is just minimal coupling, right? Just minimal coupling of the Lagrangian. So this is my quantum mechanics Lagrangian. Now when I compute the momentum conjugate to xi, okay, when I compute pi I, that is equal to m xi dot minus EAI.
Okay, a multiplies E as well in this way of doing, but
Thank you.
I mean, it doesn't matter.
Yeah. Okay. And therefore, however, the Hamiltonian of my system, okay, the Hamiltonian of my system is
X dot squared minus x dot times EI.
what? Say again?
No, in the traditional way, it's to write x dot squared minus x dot times E x dot times A.
Yeah. Thank you.
I mean, this would not give what.
Thank you. There's an extra AI squared. You're right.
The minimal coupling is just EV dot A.
Thank you. What we want to do is to write down x. Thank you. I was getting confused. What we want to write down is x dot squared by 2m x dot squared, but plus the integral of A over the well.
Yes.
Thank you. I was getting confused. Yes, integral.
Yes.
Which will be AI dxi.
Yes.
And in this case, thank you. So let me write that. I was getting confused. Thank you. So that's what xi dot squared plus, let's say, E AI xi dot dt. Okay, and then this will give us m x. Thank you. Pi I was equal to m xi dot plus E AI. right? Because I differentiate with respect to xi dot. Okay, and now I write down my Hamiltonian. So the Hamiltonian is what? It is, of course, it just drops this term. So in terms of xi dot squared, h is equal to m by 2 xi dot squared. But then I have to substitute it in terms of this pi. Okay, so h is equal to pi I minus EAI, whole thing squared, 1 by 2m. Now suppose E was equal to 1. Okay, so E is equal to 1. So H is equal to 1 by 2m pi I minus AI, the whole thing squared. Okay? Now, as usual, pi I is the object that goes over to del by del xi. Okay? Then because of periodicity, pi I is quantized. So pi I has to be equal to n by r in this case. So now in this case, there's just one I, one circle. Yeah. So pi has to be n by r. Okay? But that means that this quantity, which was basically xi dot here, yeah, was n by r minus ai. Sorry, yes, n by r minus ai. So my Hamiltonian is equal to n by r minus ai, the whole thing squared, 1 by 2m. This is the spectrum of my Hamiltonian. Now if we substitute in a is equal to wherever that was, a, so there's just one a is equal to 2 pi r alpha, maybe I don't want to.
A into capital A into 2 pi r is alpha.
Thank you, a into 2 pi r is equal. A is equal to 2 pi r. Thank you, 2 pi r times a is equal to alpha. So then we get, maybe I won't put the 2 pi. So I want alpha to go from 0 to 2 pi, let's say. Let me, okay. So just to make it look nice. So this is 1 by 2m into
2m r square into n minus alpha whole square.
n minus alpha whole square. Now this something's wrong. I've got some 2 pi's off because here.
Or maybe n over 2 pi r.
Was it n over 2 pi r? No, it was. Just a minute. Just a minute. Yeah, I've got some 2 pi's off. Just give me 1 sec. We had e to the power I p x. X goes to x plus 2 pi r.
That's
So
n by 2 pi.
n by, thank you. Yeah, thank you. And yeah.
X goes from 0 to?
X goes from 0 to 2 pi r.
No, then it will go.
Then it's just n by r because
N by
it
R.
should be
Yes.
2 pi periodic.
Yes.
Okay. Now where else have I messed up? AI.
Maybe for this case, alpha goes from 0 to 1.
But you're right, alpha goes from 0 to 1, yes. Because the holonomy, it should be when the holonomy becomes 2 pi, that is like having nothing. Yes. Fine. Alpha, in my normalization, right, so let me tell you what I'm secretly thinking. What I'm secretly thinking is this, that when I have the really gauge invariant variable is
The I,
integral a dx.
yes.
When that becomes 2 pi, that's like having nothing. But as Schumann said, when alpha is 1, then this, 1 by r, then this becomes 2 pi r by r, which is e to the pi I 2 pi, which is like having nothing. Exactly. So with this, with this choice of variables, alpha really ranges from 0 to 1. Now you can see that alpha really ranges from 0 to 1 even in the spectrum. Because, suppose you take alpha from 0 to 1, the spectrum doesn't change. Because the spectrum is all integers divided by r, the whole thing squared. That remains all integers divided by r, the whole thing squared. But what happens is that the old integer label, the label of the old integer that labels the spectrum, gets shifted by to the new integer that labels the spectrum by a shift of 1. So as you take the holonomy of the theory and increase it by 2 pi, the theory hasn't changed. It's just that you get the same spectrum, but with a different set of labels for the energy states. This is a general phenomenon. This happens often when you can change a parameter and come back to the same theory. You have to come back to the same theory, but you need not come back to the same labeling of the theory. Okay, and then this phenomenon has a name. It's called spectral flow. Again, it happens in a more interesting and complicated way in conformal field theories, which we will study at some point. Okay, excellent. Fine. So what have we concluded? We've concluded that this holonomy affects the spectrum of particles. Even though it was pure gauge, locally, it's not unphysical. We see that because it affects quantum mechanics. Okay? And we see that it affects quantum mechanics in a relatively simple way. All modes, all modings, the modings of x, the x field itself, as opposed to the pi field, okay, the periodicity is shifted to n minus alpha. Okay, at least the spectrum is as if you had modes, as if you had fields, which were moded not with n, not with integers, but n minus alpha. Is this clear? Okay, excellent. So this is what happens when you've got a charged field. By the way, I'll leave it as an exercise for you to work out the same thing in quantum field theory. Okay? Suppose you've got a quantum field theory, it's the same thing. But suppose you've got a quantum field theory, find the multi-particle spectrum of a charged scalar field on a circle, okay, with holonomy alpha. Okay, there's no canonical conjugate momentum and so on. It's just finding the energy and diagonalizing it. You'll get something for each particle, you'll get a formula like this, and then you get multi-particling of that. Okay, it's a simple exercise which I'll leave for you. I'll leave you to do. Okay, excellent. So this is what we had when we had a charge field in a U1 theory on a circle. Now, what about we've got these strings, these D-Branes, and we've got open strings that have I, j indices. I was the index of the beginning part of the string, and j was the index of the end part of the string. And you remember that the open strings were transformed in the adjoint of this UN, such that I was a fundamental index and j was an anti-fundamental index. All this you remember. Now, what we have is this kind of holonomy distribution. So suppose we've got an ij string. It behaves as if it is an effective charged particle. But the effective gauge field it sees is alpha I minus alpha j, because it's charged +1 under the ith gauge field and -1 under the jth gauge field, because that's how an adjoint behaves. The two ends, one end of the adjoint is the fundamental, the other end of the adjoint is the anti-fundamental. We've got something that's diagonal. So it's just under each of these U1s, fundamentals are charged +1, +1, +1. Anti-fundamentals are charged -1, -1, -1. So this guy goes from is fundamental under the ith guy, anti-fundamental under the jth guy. So it has an effective gauge field alpha I minus alpha j. Okay, so let us remove this here. And so now in our situation, when we compute the charged spectrum, you remember when we were doing string theory, We got non-relativistic quantum mechanics for the non-relativistic quantum mechanics for the open string. Can anyone remind me what the effective mass was?
For the open string, the action was 1 over. Oh.
The effective mass is 1 over 2 alpha prime. Why? Because we had 1 over 4 alpha prime pi.
Yeah, and then the
Multiply by
pi.
Pi. So, and then we're supposed to write 1 over 2m times m by 2. So 1 over 2 alpha prime. So we will get the part of the Hamiltonian that comes from the zero mode sector is 2 alpha prime, so by 2. Okay? And then n minus alpha I minus alpha j. So divided by r, the whole thing square. The zero mode part of the Hamiltonian is replaced by this. Is this clear? All good? Okay. Now, so this is what we have when we have open strings on a circle. Okay? We've got the really interesting physics has to do with these holonomies. These holonomies give you funny spectrum in the open string in the zero mode sector, and the funny spectrum depends on your Chen pattern indices in this form. Okay? Now what we want to do is to understand how this works under, by the way, the fact that we've turned on this holonomy effectively Higgses down a U1 gauge group to U1 to the power n.
The UN gauge.
UN gauge group to U1 to the power n.
Diagonal to its Cartan.
To its Cartan. Because the remaining gauge invariance is the part of the gauge symmetry that leaves this holonomy unchanged. But what gauge transformations leave a diagonal matrix unchanged? Unless two elements of the diagonal happen to be equal, the gauge transformation that leaves it unchanged is just U1 to the power n. On the other hand, if two of the diagonal elements happen to be equal, then you will get U2
times U1 to the n minus 2.
To the n minus 2. Three of them happen to be equal, you get U3 times U1 to the... If 3 and 2 happen to be equal, you get U3 times U2 times U1 to the power n minus 5 and so on. Okay, but in general, if you take these all to be unequal, this gauge configuration has taken a UN gauge theory and has spontaneously broken down the UN to U1 to the power n. Okay, so some sort of Higgs mechanism is going on here, because there's we said that this holonomy was a massless mode, carried zero energy. We could turn it on at no cost, okay, and get these and get reduced gauge symmetry. Okay, this is sort of like the usual Higgs mechanism. In the Higgs mechanism that you're familiar with, you have some sort of potential for the scalar which forces the scalar to take some value. What's different here is that we've got a flat potential. So scalar could have been at 0, in which case the theory would have been unhiggsed. The scalar is a Wilson line. Okay? But it could have been somewhere else. It has to be diagonal, because there's a potential away from this diagonal value. Okay, when there's only one, there's no question of being diagonal. Every matrix is diagonal. But if there were two of them, they have to be simultaneously diagonal. They have to be commuting, because otherwise there'd be field strength. That gives you a potential. So, but all simultaneously diagonal values of A are as good, and the simultaneously diagonal values of A in general break down UN to the power 2, U1 to the power n. Okay, great. All good.
I have one question. So
please.
This alpha assumes only it can assume only integer values.
No, alpha assumes arbitrary values.
Oh yeah, that's what. Okay.
Okay, let's.
Yeah, it's a fundamental domain.
Yes.
Yeah.
Yes.
No, but in that sense, I'm confused by your what you said that this spectrum is left unchanged there. Because if alpha is non-integer, the spectrum definitely changes.
Yes.
Earlier it was some integer square, now it's integer minus something.
But the spectrum is left unchanged if alpha goes to alpha plus integer.
Okay, right, okay.
The operation of taking alpha to alpha plus integer leaves the spectrum unchanged. But the operation of turning on alpha to an arbitrary value certainly changes the spectrum.
Yeah.
Okay, that's why the arbitrary values of alpha are physical, but actually shifts of alpha
integer shifts
are nothing. Okay, great. So let's keep going. Now what we want to do is to understand what happens to this theory under T-duality. Okay? So let us remember we had x is equal to xl plus xr. Okay? So we had x is equal to xl plus xr. And T-duality was the operation to move to a new scalar field x prime, which was equal to xl minus xr. We looked at the same theory, but in terms of the new variable x prime, such that the left moving part of x prime was the left moving part of x, and the right moving part of x prime was minus the right moving part of x. Now the first thing we're going to do is to see what happens. We know what boundary conditions this guy. So XL was, let's say, we'll give it some convention. Let's say that this was sigma plus tau, or maybe sigma minus tau minus sigma. XL depended only on tau minus sigma. XR depends on tau plus sigma. Okay? Now the first thing that we're going to do is to see what the boundary conditions for x imply for the boundary conditions for x prime. So what were the boundary conditions for x? The boundary conditions for x were del sigma of x was 0 at the edges. But del sigma of x is del sigma minus del sigma xl plus del sigma xr is equal to 0 with our conventions. Let me say.
XL prime minus XR.
Yeah, exactly. Minus XL prime plus XR prime is equal to 0. Okay, but this is same as minus XL. Okay, call it twiddle. Twiddle prime. Okay, minus x twiddle r prime is equal to 0, which is the same as del by del tau of x prime of x twiddle is equal to 0, because tau occurs with the same sign in left and right. So we see the first interesting thing. The first interesting thing is that under T-duality, the Neumann boundary condition, the condition which was that at the edge the normal derivative of the string vanishes, changes into the statement that at the edge the tau derivative of the string vanishes. Tau derivative of x vanishes. Now, tau on the edge runs like this. What does it mean that the tau derivative of x vanishes on the edge?
X itself vanishes.
X is constant.
Constant.
Okay? And therefore, we have T-duality mapping us to a new boundary condition. What we have is that x prime, x twiddle of 0 is constant. So let me say it more, sigma tau is some fixed number at 0 tau. 0 tau is some fixed number. Let's call it x naught. Okay? And x twiddle at 0 at pi tau is some other number. Why not? I don't know. Do you see this is not something we chose? It just happened because of T-duality. Now, if you go back to our, in fact, we can just do it again. If you remember, right at the beginning when we were first talking about open strings, we looked at possible consistent boundary conditions for open strings without adding new degrees of freedom at the open string. So we required that the variation of the action work even at the boundary. Okay? And that gave us two possibilities. Let's remember how that worked. What we have is x dot squared minus x prime squared. Okay? Then we varied this action. Okay? We varied this action, and from here, since we're looking at the boundary at sigma, we don't care if the boundaries are 0. But here there was a boundary term because there was a delta x prime, okay? And that then became at the boundary, it became at the boundary, so then we integrated by parts, and we got a boundary term which was delta x times x prime at the boundary. What? No. See, we did the total derivative term. This was del sigma of delta x prime minus the x double prime. The x double prime was the equation of motion. Okay? But the boundary term we had to make sure itself vanished under variation. And that gave us two possible boundary conditions. We so far have been working with this guy. The x prime is equal to 0. But there was another possibility, namely that delta x was 0. When is delta x 0? If the value of x at the boundary is fixed. That was always a second possibility. And if you remember when we first started talking about open strings, we said we will discard this possibility for now because we want a Lorentz invariant theory. And if x is fixed, it has to be fixed at some value, and there is no Lorentz invariant value at which x can be fixed. So that was all very reasonable. But now you see, now we've graduated beyond Lorentz invariance because we are working on a circle. Circles break Lorentz invariance. Okay? And now we're saying that by being T-duality on the circle, we're being forced in the dual description to get this other possibility. Namely that x is fixed on the circle, at the edge of the circle. Okay? So this is a key lesson, and I'll say it in words once again, that Neumann boundary conditions under T-duality map to Dirichlet boundary conditions. Is this clear? Okay? At Dirichlet boundary conditions means that the edges of the string is fixed. Now, so far I've been pretending there were no Chan-Payton factors. But if there were Chan-Payton factors, there's no reason why the fixed values should be the same for different Chan-Payton factors. So the ith string, if you've got an I on the left, an I coordinate on the left, that can be fixed at some position xi. And a j on the right, that can be fixed at some fixed position yj. Okay? So the boundary condition in general is that x in the ith sector, in the ijth sector, x at 0 is equal to x naught I, x at pi is equal to y naught j.
Why is this reasonable? Because the Chan-Payton is an internal degree of freedom living only at the physical boundary of the open string.
Yes.
And the physical boundary of the open string has a fixed coordinate which seems like should not depend on I, on that particular internal degree of freedom.
But you know, what we've got is an n squared different copies of the same Hilbert space.
Yes.
And in each of these copies we can just work with different boundary conditions. Okay, but you know, if this is not completely convincing, you'll soon see that this is forced on you by T-duality.
Okay.
This will be the dual to the statement that ij's see different holonomies.
Okay.
Hang on for a minute. You'll soon see an interpretation of this. Okay. It's very reasonable when you think geometrically. Okay, but let me get there. Let me get there. And it's okay with all the rules. Okay, let's get there. Okay. Now, the next thing we're going to see, so these are things that are just allowed, abstractly I'm saying, but let's be guided, Upman is uncomfortable and it's reasonable if you're uncomfortable, so let's just be guided by what we get from T-duality. Okay? The next question I'm going to ask is this. I'm going to ask in this string, in this x prime, okay, I'm going to ask in this x prime, what is the value of del sigma x prime from 0 to pi? Okay? I'm going to ask this in the Chen pattern sector IG. Okay, now how do I compute this? Well, we know how to compute this because del sigma x prime, del sigma x tilde up to a plus minus sign is del tau of x. Okay, I'm not keeping track of the plus minus sign, that's irritating and not very important. So that's the same as 0 to pi of del tau of x. Okay? But now what is del tau of x? So let's see. In fact, del tau of x was this quantity. It was x dot, if you remember. Basically, the Hamiltonian was m by 2 x dot squared. And then we wrote x in terms of pi. This was x dot. Okay, so up to some plus minus sign, which I'll assume is plus. In this state, in this nth state, this was equal to 0 to pi of n minus alpha I minus alpha j divided by r. All good? Now all these are constants, so the integral is trivial, so this is pi times n minus alpha I minus alpha j divided by r. I'm somehow missing a 2 somewhere. Okay, let me get my algebra and then we'll fix it. Okay, we have n minus alpha I minus alpha j divided by r. But now I want to word this in dual language. Okay? So I'll write this as, wait, and the whole thing was divided by r.
Yeah.
Okay? I'll write this as, remember that this goes to alpha prime. So the new radius, r tilde,
Alpha prime over r.
is equal to alpha prime over r. So r is equal to r tilde over alpha prime. Yes. So this is equal to, in terms of r tilde, this is equal to pi r tilde into n minus alpha I minus alpha j. Now I wanted a 2 here. Where did I miss my 2? Sorry, just a minute. Let's see if Pulchinski has this algebra. That'll be the fastest way of getting it. I'm sorry. It was in my, when I told you that this was alpha. Let's do that more carefully. Let's get del tau more carefully. So pi minus ai, that's what this was. This was pi minus ai. Okay, but that wasn't alpha prime, alpha x dot itself. That was equal to mx dot, which is m is 1 by 2 alpha prime x dot. When ai was 0, for instance, pi was x dot times mass, and mass was effectively 1 over 2 alpha prime. Right? So sorry. So x dot was this times 2 alpha prime. So this quantity, this was pi, right? In the absence of a gauge field, it was pi. This is the thing that was periodic, right? I'm sorry, I missed this factor of 2 alpha prime. So this whole thing here, this part was correct, this is correct, but this has 2 alpha prime.
There's an alpha prime from below which cancels later.
Ah, lovely. Yes. There's 2 alpha prime and then 2 pi r tilde. How lovely. Okay. Okay. Now what do we see? Let's first take the case where I was equal to j. Let's first take the case I is equal to j. In that case, what is the length? What is the mass of the string? The mass of this, what is the length of the string? So what is del sigma x tilde? What does it mean? It's the extent to which the string has stretched, going from one end to the other.
I see.
Right? But what is it amounting to if alpha is equal to alpha j? It's amounting to 2 pi r tilde n. Now, we know that the string has a particular beginning or end point, because we've got Neumann boundary conditions have gone to Dirichlet boundary conditions. Okay? When I is equal to j, what we are seeing is that the beginning and the end point are the same. Right? So that the string can go round once, or twice, or thrice, and then come back and end at the same point. Is this clear? That's the only reasonable interpretation of this fact. Let's stick to I is equal to j first. So what we've learned is that the T-dual of this description is that the II strings, the strings with Chan pattern factors I at the beginning and I at the end, begin and end at the same point. So that the allowed windings are 2 pi r tilde, or 4 pi r tilde, 6 pi r tilde. Now, what about the ijth string? The ijth string,
They can end anywhere.
be careful. You see, there is this fraction of this. Let's say that this is alpha 1. This is a position alpha 2, which by alpha is measured like a fraction of 2 pi. So the angle here is 2 pi alpha 1. Let's do angles this way.
Yeah.
So suppose that we mark the angles 2 pi alpha 1, 2 pi alpha 2, 2 pi alpha 3, and so on. Now, let's take the windings this way. Okay, I'm going to get the relative signs all messed up because one way or the other. Please ignore that. Please forgive that. Okay, so let's look at the guy going from alpha I to alpha j. It has to go a distance 2 pi alpha I alpha j times r tilde. But it can do that and then come once more around or twice more around. So it can do 2 pi r tilde n, that's the number of extra times it winds, plus or minus depending on the minimum distance it has to go. So do you see that the T-dual description of this object now is a set of n distinct positions on the circle? These n distinct positions are 2 pi r tilde alpha 1, the angles, 2 pi r tilde alpha 2, positions, 2 pi r tilde alpha 1, 2 pi r tilde alpha 2, 2 pi r tilde alpha 3, up to 2 pi r tilde alpha n. These are n distinct positions, and the rule is that the ith string, the ijth string, begins at 2 pi r tilde alpha I and ends at 2 pi r tilde alpha j. Is this clear? Okay, that's clear from that rule up there, from what we've derived. Del sigma of x, this has to be. So now we've derived the effective boundary condition T dual to this. The effective boundary condition is that every string with an ith beginning point, look at the alpha ijth string. Every such string begins at the same point, at a point determined only by its I index. And every such string ends at a point determined only by its jth index. Okay? What were these points? They were these alpha i's. In fact, they're converted to position by multiplying by a factor of 2 pi r tilde. So, Wilson lines, what have they done on the circle, on the T-dual side? They've become distinguished positions on the circle where strings can begin or end. Note that there are not n square different Wilson lines. It's not like the right rule is to have completely independent structures for every ij position. There are only n different Wilson lines. The beginning and end points are determined by the ith index and the jth index. So if the 1,3 string begins at some position, the 1,4 string also begins at the same position. If the 2,4 string ends at some position, the 1,4 string also ends at that same position. There are n distinguished positions. These n positions are called the n locations of the D-Brane. So first, what do we have here? What we have is special positions at which strings can begin or end. These special positions are in space-time codimension 1 objects, right? Because they extend over all of the other directions of space, but there's some fixed position of this distinguished x tilde coordinate. Is this clear? Okay? What you should imagine, and we will see this as we build up, that what's happening here is that there is an object. That object is called a D-Brane. That object is located at some position on the circle. Originally, when all alphas were 0, we had n objects. And they were together. All at the same position, let's say 0. That's T-dual to the configuration with no Wilson lines. Okay? As you start separating these objects, okay? Now you've got these n objects can be independently put wherever you want. Okay? And now the ijth strings are the strings that stretch from the ith object to the jth object. Okay? So you imagine that there is a stack of n different things. And the reason that you had n squared different strings in your system,
Because there are n square ways of
connecting one to the other. Okay? This is how you should think of D-Branes. Is this clear? Okay? We're going to see some of this coming out in equations as we go along. But this is how to think about it. You see just the simple rules. If you allow open strings on a circle, and you have these holonomies as you must, then the simple rules of T-duality force you into considering these other boundary conditions, these Dirichlet boundary conditions, in this very special way. The special way is that there is these locations for these objects, okay, and there are n of them. Is this clear? Now we'll see this more and more as we go on. This is just a first brush. Okay?
So the different IG sectors, I should think of them as different physical strings.
Yes, string stretching from the ith D-Brane to the jth D-Brane.
Not like one string and degree of freedom than the other.
Not what?
So just one worksheet, the degrees of freedom, then here and there.
Yeah, but the degrees of freedom. Yeah.
Like internal as Oli was.
Yeah, these degrees of freedom which were abstract in the first picture.
Yeah, so that's what I mean. So this in the original X picture, in the non-p-dualized picture, in the original frame, they would.
They were internal degrees of freedom, but there is another way to think of those. You think of it as space-filling D-Branes. Imagine that you've got n different 26 branes. Now the thing about these 26 branes is you cannot separate them because there's no direction in which to separate them.
25 brains.
25, sorry. Sorry. Sorry, you're right. 25 brains. There's no direction in which they can be separated. She can't see. It's hard to view them as different objects. That's why these indices look a little abstract.
I see.
But
Yeah,
they're always.
they were free to move around in the original picture because there was this Neumann boundary condition.
The strings were free to move around.
Yeah.
And therefore, the branes were everywhere.
Huh.
Because the strings end on the branes, the Neumann boundary conditions meant that they were free to end anywhere. So this was a 25 brane. There were always n 25 branes. Only we didn't sort of see that, because the way we see that they're different objects is by separating them. Here there was no room to separate them. But there's a fantastic thing, that is, T-duality has the property that it takes a D-Brane that's extended in the direction in which you're T-dualizing
To the codimensions.
and makes it localized in that dimension. That's what we've just seen.
Yeah.
And therefore, objects now, if there really were n different objects, we can see it by separating them. And that's how it works. Now, I told you that, look, in the first description we couldn't really separate them. In the second description we could. Yet, the two descriptions are descriptions of the same physics. So if we can separate them in the second description, there's something we can do in the first description. What was that something? It was the Wilson line. We could turn on a Wilson line along the circle, and you see that this alpha of the Wilson line is what maps to the position of the D-Branes. So in some sense, you see, okay, as we will see, there will be a world volume theory on the D-Branes. We will see all of this very soon. Okay? These world volume theories will include some scalars. Okay? The scalars will have the interpretation,
Transverse.
yeah, as being the positions of the endpoint of the branes. These positions can fluctuate around. The zero mode of the scalar will be really moving the brane. There will be fluctuations which will be oscillations of the brane. Just like a string can oscillate. Okay? Now, as we will see, there is a potential for these scalars that is like xi commutated xj, the whole thing square. Right. These are n cross n matrices. This potential, in order to minimize this potential, all these xi's have to be simultaneously diagonal. That's the dual statement to the fact that these holonomies.
Yeah, that's the Higgs.
Exactly. But being simultaneously diagonal, we can make these one, as long as they're simultaneously diagonal, we can make the eigenvalues of these x fields anything we want. Changing these eigenvalues is moving the branes. But from this point of view is Higgsing the gauge group. You see, so the invariant physics, moving the branes is our picture of what's happening. The invariant physics is that un is being Higgs down to u1 to the power n. And that we saw anyway in the first description from the holonomies. There was something that was allowing us to Higgs it down to u1 to the power n. And this u1 to the power n was essentially the fact that there were n objects. So in some sense, if we were clever enough, from the first picture we would have seen that there were n objects. But of course, it's much more visually clear and much more somehow intuitive in the T-dual picture. The n objects, and we see the n objects because we can move them. That's what we mean by n objects. We move them separately. Okay? Great. So, what we've seen is this lovely thing that T-dualizing open strings on the circle gives you special locations where strings can end. These locations are called D-Branes. Okay. Now, there are many things we have to still understand. Okay. The first thing is this. Look. Let's look at open strings on the circle. I told you that there are no winding modes for open strings on the circle, because open strings are free to end anywhere, so you can't wind them. They can freely shrink to 0. Okay? But the momentum modes are quantized. And now you might think this is a paradox, because you remember when we looked at closed strings, we learned that very small circles were the same as very large circles. The way that worked was that
both W and N.
Exactly. That very small circles had very heavy momentum modes but light winding modes. Very large circles had very light momentum modes but very heavy winding modes, and these two map to each other. How can it now work when you have only momentum modes and no winding modes? Well, the only way it can work is if in the dual description there are only winding modes and no momentum modes. But that's how it works. Because you see this.
It is from one D-Brane to other and eventually just counts.
So clearly there are winding modes, we've seen that. Also there are no momentum modes. Why not? Because a momentum mode is motion of the 0 mode.
Yeah.
But the 0 mode is not free to move because it's fixed. Right? So the way it works is that for closed strings we had both momentum and winding on either side. Momentum back to winding, winding back to momentum. Here in one picture we have only momentum. That's the original picture, the picture with no D-Branes or space filling D-Branes. We had only momentum. And in the T-dual picture we have only winding. And this continues to work. If you have a very small string, very small original circle, the momentum modes are very heavy. This maps to a very large T-dual circle, and the winding modes are very heavy. If you have a very large original circle, the momentum modes are very light. This maps to a very small T-dual circle, and the winding modes are very light. Okay? All good?
And this D0 branes, these are D0 branes, right?
No, these are D24 branes.
No, on the T-dual picture.
In the T-dual picture, they're D24 because we've not changed anything in the other directions.
Okay.
Right? Had we had the whole every direction on a circle, and had we T-dualized in every direction, then we would have got fixed positions on each of the circles. And then they would have been 0 branes. Okay? They're 24 branes because their world volume has 24 spatial directions. Because the strings are free to move anywhere in the other 24 directions, but at fixed location in this one direction. Okay. Now we've seen that these string theories on a circle must have these D-Brane objects, because you can get it by T-dualizing something without, if you had Chen pattern factors, must. But now, once we've got this, what we can do is to take the original circle size to 0. That takes r tilde to infinity. That's like having the theory without the circle. But we can do it in a way, while taking this to infinity, we can do it so that the positions of these D-Branes stay fixed.
Yeah, I mean, these are just angular positions.
These are angular positions, but what we will do is to choose alpha prime to be a divided by r tilde, so that the absolute positions stay fixed. Right? Because these in position, these are r tilde, r tilde, r tilde.
Yeah.
So if we choose alpha prime to be ai divided by r tilde and keep ai fixed as r tilde goes to infinity, then we've got a bunch of branes in non-compact space, which remain fixed. Okay? And since there's nothing stopping us from taking R to 0 in the original picture, it must be that even in non-compact space, it's consistent to study these objects at D-Branes. Okay? So we've discovered that the bosonic string has this new sort of sector, which we're forced to consider, because starting with a description without these objects and performing just an identity duality map on it, we recover these objects. Okay? These objects are D-Branes. I also told you we didn't look at it in detail, but of course you could perform, if there were many directions, many dimensions compactified, if many different dimensions were compactified, then what you could do would be to t-dualize on all these compact dimensions, or several of them, and by that trick obtain D-Branes of any world volume dimension you wanted. We got D24 branes, but by doing t-duality on 2 circles, we'd get D23 branes. By doing t-dualities on 3 circles, we'd get D22 branes, and so on. All of these D-Branes exist in the bosonic string. We will see it's a bit more complicated in the superstring. There are 1 or 2 differences in the superstring. But is this clear? All good? Okay? So all these objects exist, even in the non-compactified theory, because we can take each of the new circle directions to infinity in the end, keeping these branes fixed. So they're all objects that are present in string theory, as is seen by this almost trivial analysis.
And so far we have not considered the dynamics of D-Branes themselves.
Not yet. We'll soon do that.
This alpha 1, alpha 2, they are all fixed. Once and for all.
Yes. Now it's a very important question. Do D-Branes themselves have dynamics? And the answer to that question is yes. How do we know that? The first question we want to ask is one question we're going to ask is what are the vertex operators for all massless modes in the D-Brane theory? So let's look at what the vertex operators were for the massless modes before compactifying. Before t-dualizing. Okay? These vertex operators, as we said, were basically del x. Okay? Now, let's remember more carefully. Vertex operators are boundary operators, right? Okay? So suppose we were, suppose we're looking at the boundary of a string. So that this is tau. Yeah. And this was sigma equals 0, for instance. Maybe I should have drawn it. Let me draw it the other way. I'm drawing it this way because you think of it the half plane, but okay, it's conceptually clear this way. So suppose this was tau, this is sigma equals 0. Then the vertex operators was lay on that boundary, and therefore was del tau of x. Del sigma of x was 0, so that couldn't have been the vertex operator. That was a Neumann boundary condition. But del tau of x, the derivative along the boundary, was non-zero. That was the usual vertex operator in open string theory. Inserted, remember, on the boundary. These were the vertex operators dual to the open string states. Okay? Now, what does this map to in the t-dual picture? Well, we've already seen the delta of x. Exactly. This maps to?
Maybe with a sign.
Exactly, with some sign. Del sigma x tilde. Makes a lot of sense, right? Because it couldn't map to del tau of x tilde because del tau of x tilde was 0. So it maps to del sigma of x tilde. Okay? So now there is some vertex operator for this guy here. There is some vertex operator, And the question that we want to understand is, what is this vertex operator physically? Turning on, like taking this vertex operator and dressing it with an e to the pi ki xi. So if we take del sigma of x times, let's say, e to the pi ki xi are the other directions, such that k squared is equal to 0, gives us a good physical state operator in string theory. It's the dual to this guy. Okay? Now, this guy was, what was the interpretation of this operator? This vertex operator was dual to the
Photon.
the gauge field, exactly. And if we took the zero mode of this operator, it was the vertex operator dual to the Wilson line. Okay? But, okay, let's see it in many ways. But of course, it's already sort of clear to you that this now, the zero mode of this operator is going to be dual to whatever was dual to the Wilson line, which was the position. So there is a vertex operator corresponding to moving the position. More precisely, if you take this operator with this fluctuation, what will it now be? It will be motion of the position in a way that depends on the transverse coordinates. So what it will be is taking this D-Brane and having its position, which was fixed, have it ripple. Is this clear? Is this clear? Therefore, that immediately establishes that the D-Brane is a physical object, because the position of the D-Brane can be moved. Now you can question, is that moving, because it's a zero, it's some k equals 0, it's very special, it's really a physical object. But you can't dispute that this guy is physical. And there's a vertex operator corresponding to it. Okay? Now, it's like understanding of Goldstone's theorem, right? If you can move something everywhere and go to spins rotating a little, then we move this with a long wavelength. Locally you're rotating the spins, but with a long wavelength. Okay? This we know is a massless mode. What is the interpretation of this massless mode? It's taking this D-Brane and moving it here, but how much you've moved it depends on where you are in the transverse position. So let's be a bit concrete. Suppose x2 was the direction of the circle, and we turn on an e to the pi k x1 minus k0 x0, and we look at it at fixed time. What will it look like? It will look like position on the circle. So let me draw the position of the on the circle on the y-axis, and the position in x1 on the x-axis. It will look like this, right? So the position of where the D-Brane is, where the strings end, fluctuates with x1. This immediately establishes that the D-Brane is a physical object. Because what does it mean that it's physical? It means that it can vibrate around. But that's what's happening. This vertex operator, the vertex operator del sigma x, is precisely the operator that sets it into vibration. Okay, now let me leave the following thing as an exercise for you. Take the string action and add to it alpha in the exponent alpha epsilon times del sigma x, where epsilon is small. So we're just deforming it by a vertex operator. Okay? Show that is equivalent to changing the position of the D-Brane by epsilon. It's basically the same algebra we've gone through here in some language. Okay, but just show that. It's basically, okay. It's almost trivial, but. Okay. So this, of course, we're going to see it in many different ways as we go along. But this already roughly answers your question. D-branes are dynamical. They're dynamical because there is an open string degree of freedom, part of the spectrum of the theory, that represents the vibrations of the D-brane. In fact, this gives us a great new interpretation for this del sigma of x. It is the mode that creates ripples of the D-brane. Okay? So the D-branes can, every time you T-dualize, suppose you've got this 25 brane, and you T-dualize 5 times. Then there are 5 distinct such modes. And that's great. That's exactly what you expect, because now this is an object that is localized in 5 directions. So it has 5 distinct vibration directions. It can vibrate like this, or like this, or like this. So these different modes are all these different vibration directions. Just like a string can vibrate in 24 directions. A DP brane can vibrate in 25 minus p directions. Because it's localized in space in those many directions, those are the directions in which it can vibrate. And for every such direction, there is a vibration mode. So it shows you that these D-branes are dynamic. Is this clear? Okay, wonderful. Now let us try to understand more about these D-branes. Not sure how far we'll go, but let's start. First, any questions or comments? I know this is new for you. Questions or comments on this? Okay. Okay. Now, the next thing I want to do is to explain to you that this dynamical nature of the D-brane can be taken very seriously. In fact, we can write down a world volume action to quite high accuracy describing the massless modes on the D-brane. Okay? I'm going to first write down the action for you, and then I will argue every element of it, maybe next class. But let me write this down for you. Okay, this is the action. The action on the P brane is given by minus TP dxp plus 1 e to the power minus 5 minus det of G AB plus BAB. Where TP is something that we will soon proceed to determine.
This is the DBI action.
This is the DBI action. Okay? So first let me explain what all these terms mean. You see, what are the massless degrees of freedom on... So at the moment I'm looking at now just one D-brane, okay? Not a collection of many of them. What are the massless degrees of freedom on a D-brane? Well, these are one-to-one correspondence with the massless vertex operators of open string theory. We've got gauge fields in the directions of the D-brane. Because, you see, I told you that del tau x went to del sigma x in the directions which we've T-dualized. But del tau x remains del tau x in the directions in which we've not T-dualized. Those continue to represent gauge fields. So the fields of the D-Brane are a gauge field on its world volume. Okay, so if you have a dp brane, we've got a p plus 1 dimensional mu field living on its, right? And 25 minus p scalar fields, which represent the transverse fluctuations. Now, if these transverse fluctuations change slowly enough, we should be able to write down an action for these transverse fluctuations. Moreover, if the gauge fields are also turned on, we should be able to write down an action for this. And in fact, we should be able to write down an action for both of these things combined. Okay? And within some accuracy, I'll tell you about the accuracy as we go along. The claim is that this is the action. What is GAB? GAB is the metric induced on the world volume of the D-Brane. So we've got some space-time metric, and then we've got the D-Brane moving around here. And the metric in space-time, when given the position of the D-Brane, given the manifold, the submanifold that it's occupying, induces some world volume on that D-Brane, and that's GAB. Very much like the G that we used in writing down the number go-to action for the string. What is BAB? It's similar if there is a B field in space-time. Okay? There is an induced BAB on the world volume of the D-Brane. And so this is that BAB. And what is FAB? FAB is an intrinsically world volume object. It's the field strength of the gauge field. Claim is that this action, plus corrections, and I'll tell you what controls the corrections, controls the low energy effective action of a single D-Brane. As Upmanyu said, this action has a name. It's called the Bornenfeld action. And this is a very useful object. Okay. So now all the elements of this action I want to explain to you. The only question is whether we should do it this class or next.
Just 1%. And
yes.
At least in the determinant, this it's not manically symmetric or antisymmetric because it has a combination of symmetric and antisymmetric.
Exactly, and that's fine.
Yeah, I mean,
no reason.
No problem.
Yes,
yeah.
It's just determinant of a matrix.
Yeah.
Okay. Exactly. So if you turned off BAB and FAB, it would be completely symmetric.
Yes.
Okay. So let's
BAB is not symmetric.
what?
The BAB is also antisymmetric.
Yeah. BAB is antisymmetric as is FAB. So let's first look. Let's imagine that we've turned off all the fluctuation degrees of freedom. Okay. So we work. So we've oriented the D-Brane such that its coordinates are the space-time coordinates in p plus 1 directions. Okay? And imagine that we are not allowing it to fluctuate. So then this GAB is just delta AB, BAB, and imagine there's no B's. BAB is 0. So then this would be minus det of delta AB plus 2 pi alpha prime FAB.
Young-Mills
Now,
or Maxwell.
right. Now what we're going to do is to evaluate this determinant in an expansion. Okay? To start with, imagine that we evaluate in an amplitude expansion. Okay. So this now is determinant of identity plus 2 pi alpha prime times f. Now we're going to use this nice formula, which is that determinant is trace log. A trace of e to the power log of I plus 2 pi alpha prime f.
Exponential of date is trace.
Exponential of det is no, this is the determinant itself. Right?
The rate of exponential is trace.
Huh? Determinant of exponential is trace. See, what we're doing is basically think of it in the level of eigenvalues.
Yeah, log of
Yes,
the matrix itself.
Yes. And then when you exponentiate, you get rid of the log.
If it's inside the bracket.
Inside the bracket, thank you.
Yeah, and now that will be exponential of 2 pi
Now what I'm going to do is expand the log. Okay,
Yeah.
so
We have to expand it to second order.
to second order. So I get trace of e to the power 2 pi alpha prime f plus minus 2 pi alpha prime the whole thing squared by 2 f squared. And then ignore everything else. Okay, and then I evaluate this. So I get 2 pi alpha prime f.
There's a 1, but that is a constant.
That's a constant, exactly. So there's 1 plus. Now there's the term that is just this guy.
Yeah, that's 0.
That's 0 because f is antisymmetric. So the parts linear in f are 0. The parts quadratic in f, well, we get minus 2 pi alpha prime by 2 f squared. And then
That's a symmetric object itself.
that's symmetric, but what about this guy square? Why is it? It looks like it's cancelling. Shouldn't cancel.
No, it's not. I mean, there will be a change of factor. I mean,
No, both have half.
Both are half. Something's wrong. I've done something wrong.
This exponential of log, this
I,
formula is wrong.
is this formula wrong? Please.
Trace of it is just rate of something.
Trace up here? The trace should go up here, right? Thank you.
Trace of exponential is trace of.
The trace should go in here. Is this right?
Yes.
Yeah. Thank you. Thank you. Thank you. Thank you. Thank you. Yeah. That makes more sense. Yeah. Okay. Excellent. Now it's very clear. Now because this is 0 and this is e to the power this minus, and then we just bring it down.
yeah.
So you get 1 minus 2 pi alpha prime by 2 squared. 2 prime alpha prime squared f squared. 1, as you said, was some constant. The important point is that there was the f squared. F mu nu. Okay, so you see that at leading order and in amplitudes of this gives us Maxwell's action for the gauge field. Okay, on the other hand, suppose now we froze this guy. Okay, and we allowed we just put in flat space, but we allowed the embedding to be such that so now these are the transverse directions. Okay, is equal to xi of x alpha, which were the directions of the D-Brane. Now if you take that and expand this out, just like in Nambu-Goto action, you can do this as a little exercise. Once again, with some factors, you will get del xi, the whole thing squared, obviously. Right? This is clear, right? Right? If you take, so suppose the world volume directions were x alpha. The transverse directions are xi. The equilibrium position of the brane is capital Xi is equal to 0. Okay? Now let's look at the configuration. Xi is not 0, but it's small, and is xi of x alpha. Now we want to evaluate this determinant of GAB. Let's do it. It's a simple exercise. What's the determinant of GAB? Well, first, so what's GAB? See, the metric in space-time was exactly del x was dx alpha plus dxi. That was the metric in space-time. Now we just put in that xi was xi of x alpha. Okay, so we will get dx alpha plus del xi by del x alpha dx x alpha del xi by del x beta dx beta. So the effective metric g alpha beta is equal to delta alpha beta, that's from here, plus del alpha xi del beta xi from here.
Determinant is 1 plus del x.
Exactly. So now the determinant, when you evaluate it using the same formula as before, we'll get 1 plus del xi, the whole thing squared. Trace. Right? So what this amounts to then is a bunch of massless scalar fields at this order in fluctuations. So what we've got here is a bunch of massless scalar fields and a bunch of photons interacting with each other in this intricate way, this intricate nonlinear way. Okay? Now what I have to do for you is to justify this action. Now this will take a little time. Let's do that next class. Okay, so on Thursday we will study this action.